In the previous video on queuing systems, we developed the basic queuing network, queuing structure, and we walked through the example that we see here. At the end of the video, we had identified the three performance metrics that are of interest to us, in particular the server utilization, which we represent as rho, the average number of entities in the system, which we represent as L, and the average time that entities spend in the system, which we represent as capital W. In this video, what we're going to do is pick up and consider how we compute these performance metrics for a given queuing system. And so let's first look at the server utilization, and in doing that we want to first define something that we're going to call BT, which is the function that determines how many units of the server are busy. Since we have a single unit capacity server, this value is either going to be 0 or 1 depending on whether or not the server is busy at time t. And so if we look at the plot of BT over time, you can see here that at time A1, when the first entity arrives, the server becomes busy. It stays busy when the first entity completes because it's processing the second entity, and then here at C2 the server is no longer busy. And so our function between the time 0 and C2 looks like we see here. At time A3, when the third entity arrives, the server remains busy through the third, the fourth, and the fifth entity, and then it becomes idle again at time C5. And so if we're interested in measuring the server utilization over this time, what we want is the integral of our function BT on the interval 0 to C5. In general, what we want is the limit of this same value or this same expression as t goes to infinity. The second metric we want to look at is the number of entities in the system. So similar to BT, we're going to define LT as the instantaneous number of entities in the system at time t. And you can see that value is 0 between the time 0 and A1 when the first entity arrives. Takes the value of 1 between A1 and A2. At time A2, when the second entity arrives, it takes on a value of 2. At time C1, when the first entity completes, we then have 1 entity in the system. When C2 completes, we have 0 until the third entity arrives at A3. At A4, the fourth entity arrives. At A5, the fifth entity arrives. And so you can see at this time, right here at time A5, between A5 and C5, the value of LT is 3, representing the fact that entities 3, 4, and 5 are currently in the system. At time C3, the third entity leaves, and we have 2 in the system. And then finally, at time C4, the fourth entity leaves, and we remain with the fifth entity in the system, or we have a value of 1. And so if we're interested in L, which is the average number in system over our time interval, we simply take this integral of the function LT and divide by this finishing time. In general, we want the limit, again the same expression, that we want the limit as t goes to infinity because we're interested in the average number in system at steady state. The utilization and the number of entities in the system, the average number of entities in the system, are both what are called time-dependent statistics or time-dependent values. You can see that we're taking the integral of a function of time over the time that the queuing system operated. Our third performance metric is the average time that entities spend in the system, and to get this we just simply measure the time that each individual entity was in the system. So to get the time that the first entity was in the system, we just subtract the arrival time from the completion time. Same thing for the second entity, the completion time minus its arrival time, the third entity, the fourth entity, and the fifth entity. And then when we want the average time that an entity spends in the system, we simply take the numerical average of our 5 entities in this case. And in the general case, we want the limit as n goes to infinity. So we want the average time that an entity spends in the system at steady state. So unlike the previous two, which were time dependent, this is what the time entities spend in the system is what's called an observational statistic, because we have individual observations. In our example, we have 5 individual observations, and if we think about our calculation we simply took the numerical average, whereas in the previous two statistics, we integrated the function divided by the overall time, and so it was not only the magnitude of the value, in particular 3 as we see right here, but also the duration over which that value was enforced that mattered to us. And so we have these two basic types of statistics, two basic types of values that we're tracking, the time dependent and the observational. So in summary, we have our three performance metric of interest, rho, L, and W, and what we've demonstrated here is how to compute these values for a specific queuing instance. So we have a particular timeline where we were given a set of arrival times and service times, and using the service and arrival times we demonstrated how to compute these observed values for rho, L, and W. We also talked about the general case where what we're usually interested in is the utilization over a long period of time and when the system reaches what's called steady state. And we're interested in the average number of entities in the system and the average time that entities spend in the system also at steady state. So we can't really use the method that we did previously if we're interested in these steady state values, because we can't add, we can't do the integration over infinite time horizon, and we certainly can't compute the numerical average of an infinite number of entities. So we need to look a little bit further at the general queuing structure, and what we're going to do is talk a little bit more about the arrival process and the service process. And we're going to define the rate at which entities arrive, which we'll call lambda. This is number of entities that arrive per unit time. So for example, 10 entities per hour arrive. So rather than talking about an individual arrival time or a set of individual arrival times, we're talking about the overall arrival rate. And rather than talking about an individual or set of individual service times, we're talking about a service rate. So if we define these, lambda and mu, then we can define the utilization. Rho is simply equal to lambda over C mu, where recall C is the number, is the service capacity. And so in this case, if we have lambda equals 10, we can get a rho of 10 over C, which is 1, times 12, which is about 8,333. And so what that tells us is that if entities arrive at the rate of 10 per hour, we can process them at the rate of 12 per hour, then we're going to have an overall utilization of about 83.33%. Now, if rho is strictly less than 1, then the queuing system is what's called stable. And what we mean by stable is that the server can process entities faster than they arrive, and the number of entities in the system will be finite. Will be finite over any period. On the other hand, if rho is not strictly less than 1, then we say the queuing system is unstable, in which case it never achieves steady state, and the number of entities in the system, and in fact the time in system, will grow without bound. So we're primarily interested in those queuing systems where rho is strictly less than 1. Okay, one little thing, I had to fix this typo that I noticed previously in the video. I had that as M, and I referred to it as mu. I just forgot to set that font to the symbol font. So of course the mu is the rate at which entities are served rather than M. I had the mu here in the expression the whole time. So we see that without much information at all about the arrival or service process, all we really know is the rate, we can compute the utilization. Unfortunately, we can't do the same thing when we're interested in our other performance metrics, namely the number in system and the time that the entities spend in system. So at this point, we need to make some more assumptions about how the process works. And so some common assumptions are as follows. First of all, we have C servers, which we've already talked about. In this case, we have a single queue with first in, first out ordering. The inner arrival times are IID, which is independent identically distributed random variables, where lambda is the rate. And we also assume the service times are also IID random variables, where mu is the rate. And finally, we're also going to assume that the inner arrival times are independent from one another. So we're also going to define or use something that's called Kendall's notation for describing our queuing system. And our version of Kendall's notation, or the version we're going to use, is a reduced version. There are also other versions that have additional information, but all we're interested in for this video are the three components that we see here for ABC. So A describes the arrival process, B describes the service process, and C gives the capacity of the server. And the three values, or the three types of queuing systems that we're particularly interested in, are the MM1, the MMC, and the MG1. And in this notation, the M stands for Markovian. So an MM1 queuing system is one that has Markovian arrivals, Markovian service, and one server. An MMC queuing system has Markovian arrivals, Markovian service, and C general servers. And G stands for, in MG1, general. So non-Markovian, it's just a general service process. So a Markovian process, among other things, is one where the values are independent and has the memoryless property. In other words, knowing something about one value gives you no information about subsequent values. And of interest to us in particular, for a Markovian arrival process, the inner arrival times are exponentially distributed. For a Markovian service process, the service times are exponentially distributed. And if we make those assumptions, then we can compute the values for L that we see here, L and W. And so we see in this column we have the values for MM1, and in this column we have the values for MMC. And the derivation of these we're not going to talk about in the video. The notation that I'm using is from the Askin and Standards book, but there are many other books that also go through a complete derivation. But you can see if we can make the assumption about Markovian arrivals and service, then we can do a fairly simple computation to get the number in system at steady state, the time in system. We also have two additional values that we haven't talked about, LQ, which is the number in queue at steady state, and WQ is the time spent at steady state. If we have MMC, so if we have more than one server, then the computation is a little bit more involved, but still fairly straightforward in that we can just compute the exact values. And so, for example, if we have our previous example where lambda equals 10 and mu equals 12, and we have an MM1 queuing system, we see that the number in system at steady state is simply rho over 1 minus rho, which is going to be 5. And W is 1 over mu times 1 minus rho, and so that ends up being 0.5. If we change if we change lambda to, say, 11, then our L, we'll call it L sub 11, ends up being 11, and our W, again, I'll use sub 11, ends up being 1. Once lambda gets to be exactly 12 or greater, then we can't use our queuing formulas because we have an unstable system, because stability requires that rho be strictly less than 1. And you can see how easy these computations are. If we have an MMC queuing system, and we know the arrival rate and the service rate and the number of servers, we can simply compute the values of interest at steady state, and that turns out to be quite powerful. If we don't have Markovian arrivals or Markovian service, then things get a bit more complicated, and that's a topic for another video.